those first 30 years in order to stay one step ahead of the problem, to outpace the accumulation of damage that the therapies don't yet work on. Complicated concept in words, but very simple in the concept that I've shown you in the diagram. So then, of course, the fundamental question we have to ask ourselves is, well, okay, how realistic is it that we could actually achieve longevity escape velocity? And I would like to put a couple of arguments to you for suggesting that it's actually very likely indeed. A lot of biologists don't like it when I talk about technology that has nothing to do with biology. They say, well, this is nothing to do with biology, therefore I refuse to listen. But that's irresponsible. It's just not scientific. Scientifically, you have to take whatever data there is, however indirectly it may be relevant, and not just throw it away because you just don't like the sound of it. And the fact is, in this case, the relevant data is the rate at which technologies are typically improved throughout the whole technology, not just biology. And the key point I want to communicate here is that there are really two types of breakthrough in technology. There are fundamental breakthroughs, and there are incremental refinements of those breakthroughs. Fundamental breakthroughs, very, very hard to predict when they're going to happen. You know, I mean, Leonardo da Vinci probably thought he was only a couple of decades away from getting his little devices off the ground. And he was wrong, and lots of other people were wrong over the next few hundred years, but the Wright brothers were right, and there they are doing their thing. And I bet they were a bit surprised that it only took another 24 years for someone to fly solo across the Atlantic, but that's Lindbergh in Paris. 22 years until the first commercial jetliner, 20 years until the first supersonic jetliner. You know, it's pretty impressive and smooth. And you may say, well, okay, where's my flying car then? But of course we know the answer to that, namely we couldn't be bothered. There has not been the commercial pressure, the public interest in advancing personal commercial travel further than this point. And that's not likely to be a problem when it comes to keeping people from getting nasty diseases. And of course this is just an example. You can look at any other technology you like. You can look at computers. You can look, as you all know, at the history of the combating of infectious diseases, and you see the same sort of thing. Jenner and Pasteur didn't know terribly much about the immune system, but they sure as hell saved a lot of lives, and we've come a long way since that point. So this is pretty good news. A better argument, well, a more direct argument anyway, is to use a computer simulation. So here's my definition of aging again. A few years ago I worked with a very talented programmer in New York who helped me write a computer simulation of the mechanistic nature of aging. Actually, the accumulation of damage and its consequences in terms of probability of death as a function of age. And this is the bottom line. Obviously, this paper is published. I can perfectly happily send anyone a reprint. But here's the bottom line. The black line here is a survival curve of a natural population today. I think it's US males in 99 or something like that. So a survival curve, just for all of you who don't know, is simply a plot of what proportion of a given population are alive at any given age. So obviously at age 0 everyone's alive by definition, and then most of them hang on until age 50 or 60, then they start dropping like flies and hardly anyone makes it beyond 100. Now the dark blue line here is the simulated survival curve of the population that start getting these therapies, but that only start getting them at the age of 80. So, of course, the two lines, the black line and the blue line, are coincident until about halfway down, because only about half the population actually get to age 80 in the first place. And the ones that do get to 80 are not in a terribly good way, for the most part, which means, of course, they have a high risk of death each year relative to young adults. So, what's going to happen? Well, these rejuvenation therapies, since they're not perfect, they're not going to just instantly restore these people to youthful, good health. They're going to actually just chip away at the problem. And over a period of time, people may get to a point of becoming biologically younger, but they've got a long way to go, and the result is not very impressive. Basically, after only a maximum of about 10 or 15 years of additional benefit, the whole population's gone just because of the cumulative probability of dying each of those years when they're not in a very good condition. However, have a look at this line here, this grey-blue line. This is the simulated survival curve of a population that also got these therapies, same therapies, but got them 10 years earlier, starting at age 70. And as you can see, the story is rather different. It's not very different at all at first. You've got not much benefit, but eventually the people who do get lucky enough to get a little way out of this start pulling out of the dive. They start to get biologically younger enough that the probability of death each year goes down really quite dramatically, and maybe 15% of them get out to 150, and those who get out to 200 or so have essentially zero chance of dying of anything age-related, however long they live, just if they get the therapies that are state-of-the-art at any given time. So, of course, this graph does not incorporate representation of death from causes other than aging. If you're 60 years old when the therapies kick in, that's the brown line, and nearly half the population get out that far. So this is all pretty impressive. This is absolutely, definitely longevity escape velocity in space. But here's the really good news. The real kicker on this slide is not the diagram. The real kicker is this up here. In this particular run of the simulation, I was just ludicrously, just fantastically over-pessimistic about the rate of progress. I suggested that the therapies would double in their comprehensiveness only every 42 years. I mean, for crying out loud, 42 years. That's the time between Lindbergh and Concord. I mean, how crazy is that? There's absolutely no way it's ever going to go that slowly. So, you know, it's very counterintuitive, this longevity escape velocity concept. I'm not saying it isn't. You have to hear it, you have to think about it in order to understand it, in order to understand that it's realistic. But the fact is it's not just realistic. It's absolutely goddamn inescapable. It's going to be hard to get those first 30 years. We don't know how long that's going to take, and I'm not saying we do. I think we have a 50% chance of getting there within 25 years, but I think there's at least a 10% chance that we'll hit enough unforeseen obstacles that we won't get there for 100 years. 50% is, of course, quite enough to be worth fighting for, so that's okay. But the point is, I'm not saying that that's predictable. But what I am saying is that once we do get those 30 years, the hard part is over, and we are pretty much guaranteed to have this sort of phenomenon occurring, whether you like it or not. So it's really important to actually know it. Actually, it's even better than that. It turns out that longevity escape velocity goes down with time. The more we succeed in terms of knocking back the damage of old age and making these therapies more and more comprehensive, the more slowly we can get away with continuing to make them more comprehensive. Here's an illustration of that. So this is obviously a car that's not 50 years old, it's 100 years old. And it's getting well maintained. I'm not saying it doesn't. But the point is, it's only getting the same sort of maintenance now that it was getting 30 or 40 years ago, when it was only 3 or 4 times as old as it was ever designed to be. So, in other words, longevity escape velocity for cars is already more or less zero. And, you know, we don't have 200-year-old cars, but that's not because we don't know how, it's because we haven't invented cars 200 years ago. The cars that exist like this are very likely indeed to still be on the road in the same condition 100 years from now. So now, I want to emphasize, especially with a medical audience, that I don't work on getting people to live a long time. I've talked a lot just now about lifespan, but I don't work on that. I work on stopping people from getting sick, just like you. The only difference between what I do and what you do is that I think that we've got a damn good chance in the foreseeable future of getting so good at stopping people from getting sick that, in fact, as a side benefit, they're going to last a long time, because they'll be genuinely in the state of health that young adults are in today. This, however, is the consequence. People do insist on asking me about the consequences for lifespan. Some of you probably know that the world record lifespan at the moment is 122. A wonderful lady named Jeanne Calment, who died in the south of France in 1997, and who for the last 15 years of her life was exceptionally old and had to contend with journalists coming around and asking her the same boring question every birthday. They said, "What's your secret?" And she was a great character, and she would give a different answer every year. The best answer by far was the one that she gave when she was 120. She said, "It's because I gave up smoking when I was 117. And it wasn't even true. She only gave it up for 6 months, and then she said, "No, this is no good." Anyway, the point is, we won't get 150-year-olds, or we won't get the capacity to get 150-year-olds until we've got these therapies that confer robust human rejuvenation, those 30 years that I'm talking about. Okay. But once we have got that far, the easy part is to come, the hard part is over, so that means we get this sort of consequence, that the first people to live to 1,000 are probably not much younger than the first people to live to 150. Where do I get 1,000 from? It's not a number taken out of the air, it's the sort of age that most people on average would reach today if they maintained, indefinitely at any age, the risk of death that young adults in the West experience at the moment, you know, from causes obviously other than aging. Of course, you get a different answer here depending on exactly which population you look at, but plus or minus a factor of 2, that's what you get. So that number is real. What does this mean? Well, it doesn't mean this. I get a lot of flack from people who don't like the political correctness of all of this, and who get worried that it might actually make me sound as though make gerontologists sound as though they aren't quite real scientists. They say things like this. They say, well, this sounds like immortality, doesn't it? And immortality is sort of not the job of science, therefore this is science fiction. And I hope I've convinced you that that is somewhat an oversimplistic interpretation of what I'm telling you. But it is fair, you know, well-known and credentialed gerontologists try to say things like this, that you know, this is scientifically absurd and irresponsible. And maybe it is, but technologically it's not absurd at all, and therefore, technologically, it's they who are irresponsible. This is my favourite one. So Richard Farragher is a rather humorous gerontologist from the UK, and he introduced me for a talk saying this one. But this is my view. This is the title of a paper I wrote in 1994 that got me into an enormous amount of trouble. So I'm going to stop just by saying a word or two about how you can make a difference. First of all, I've written a book about this. So this is a semi-technical book, by which I mean it is low on jargon. There is not much in the way of serious technical jargon in this book, but it definitely